Starting off with the correct source files identification, our program makes use of the Maven file structure. So in our root folder, we have a pom.xml file, which handles all of our dependencies, plugins, which version of Java to use, as well as how to build our project. We have a source file, a source folder, underneath which we have our main folder as well as our test folder, with our main folder holding all of our source code and our test folder holding all of our unit tests and acceptance tests. Underneath our main folder, we have org.communication, which contains the client folder as well as the server folder. The client folder contains all of our code related to the client side, with the server containing server folder or server module containing all of the code relating to our server, with the main Java file on the server side being server.java and the main client side file being client.java. Then moving on to the correct versions of additional files, we have a folder called libs, which is for our external libraries, which are not available on the Maven repository itself. We have our EOD SQL jar, as well as JSON for handling our JSON requests, as well as the SQLite library. All of these paths are specified in our pom.xml file, where it will either look for our dependencies on the Maven repository itself, or use the local version if it's not able to find it there. For example, our EOD SQL dependency would look at our base directory and then inside our libs folder shown here on the left, it will then look for the jar file and include it in our dependencies. Then moving on to retrieving and updating our source files, number 3, our project makes use of Git, specifically GitLab, to ensure we keep track of our progress and make use of version control. As highlighted in this terminal below, our procedure is to always git pull before we make any push requests. This ensures that we get all of the updates from other developers, so we do not push our own code over theirs. And so we always have the latest version of the code. So we would pull and then add and commit our own code, which we then push. We do not make use of any branches. We have a single branch, the master branch, and therefore it's very important to always git pull before you push, so you don't overwrite other people's code, as we're not making use of branches to each have our own branch to work separately on. Then moving on to number 4, protecting source files during updates. It's very important for our work structure that since we do not have our own branches, that we always git pull before we decide to commit any of our own code, as this prevents loss of other commits by other developers. And then finally, number 5, preventing simultaneous updates. With our workflow, if you attempt to git push before you have git pulled, it will give you a warning that your current branch is multiple commits behind the master branch on the GitLab itself, and will force you to git pull before you are then allowed to commit.
In the robot world API class, a world object named current world is initialized, representing the current state of the robot world. The world class is responsible for managing and restoring world-related data. This endpoint retrieves a specific world by name. If a valid world is provided, it attempts to load the world using world.restoreWorld. If it's successful, it responds with the object in the world. Otherwise, it returns a 404 status with a world not found message. The method getAllObjects should return the data representing all objects in the world. And this endpoint retrieves the objects from the current world. It responds with the JSON representation of the object managed by current world. And then we have the robot world API handler. In the robot world API handler, this endpoint processes requests to launch a new robot. The request body is passed into a JSON node object. The launch robot method is then called to create and add a new robot to the world. After successfully adding the robot, it responds with a 201 created status and a JSON object detailing the successful launch. And in here, the data from the JSON node object is used to extract the robot's name and type. It checks if a robot with the same name already exists. If not, it creates a new robot instance, adds it to the simple server's list of robot names and objects, and return the created robot. The successful launch response creates a JSON response that includes the results of the robot launch and the robot state. It formats the robot's position, direction, shield, shot, status into a structured JSON object. In summary, the methods of accessing data in these classes involve initializing and managing world state, handling HTTP requests to retrieve or modify data, passing JSON data from requests to create or update robots, returning JSON responses with relevant information about the world and robots. These methods ensure that data is accessed and managed in a structured way, providing endpoints for interacting with the robot world and handling robot operations. The database setup class is responsible for managing the setup and interaction with the SQLite database used by the robot world application. Our key methods and their functions are setup ORM. It initializes the database connection and obtains data access objects for world and obstacles using EOD SQL. Create tables creates walls and obstacle tables if they do not exist, using SQL statements executed through a statement object. Add obstacle to world adds an obstacle to a database by creating an obstacle DO object and inserting it using the obstacle DAO. Save wall saves the current world instance into the database, including its obstacles. Save obstacles saves all obstacles from the current world to the database categorized by their types. And restore world restores a world from the database by retrieving its name and obstacle and configuring the world instance accordingly. And lastly, world exists method checks if a world with a given name exists in the database. We have obstacle DAI interface that defines the methods for accessing obstacle data in the database. Get obstacles by world ID retrieves obstacles associated with a specific world ID, and inserts a new obstacle into the database. And lastly, deletes an obstacle from the database based on its ID. We have obstacle DO class that represents a data object for world. And we also have world DAI interface. Overall, the setup manages world and obstacles data by creating tables, inserting data, and restoring it as needed. The use of data access objects and data objects with EOD SQL helps in abstracting database operations. All identifiers in our code are chosen to reflect their purpose accurately. Variables, methods, and classes are named descriptively, adhering to best practices in coding standards. For our classes, we use pastel case. Each word starts with a capital letter, and the names should be nouns, reflecting the role or purpose of the class. For example, database setup, world, DO, obstacle, DO, obstacle DAI, and world DAI. These names clearly indicate that database setup is responsible for setting up the database. World DO and obstacle DO are data objects related to world and obstacles. For our methods, we use camel case, and the methods should be verbs describing the action they perform. For example, start ORM method, create tables, add obstacle to world, save obstacles. These names clearly indicates the actions performed by the models. For example, the start ORM method initializes object relational mapping, and add objects to world adds an object to a world. For variables, we use camel case as well, and variables should be nouns or noun phrases that describe their purpose, like world ID, world DAO, obstacle DAO, connection, position X, position Y, type. These names reflect the purpose of variables clearly. For example, wall size denotes the size of the world, and position X and position Y denotes the coordinates of an obstacle. For our constants, we use uppercase with underscores separating words, and they should be nouns. Like insert wall SQL, check name SQL, insert obstacle SQL. These constants are named to reflect their role in holding SQL query strings. Overall, adhering to these naming conventions helped us improve the code readability and it enhanced maintainability, which reduces the need for comments and make it easier to update or refactor code. And consistent naming conventions makes it easier for all team members to understand and work with the code. Maintaining descriptive and consistent naming conventions aligns with the best practices and contributes to clean, effective, and maintainable code. Testing program development, our launch robot test class provides a comprehensive set of acceptance tests for validating the functionality of launching robots in the robot world. Acceptance tests stimulates real-world scenarios to ensure that the system behaves as expected from the user's perspective. For example, our test ensures that robot can be launched correctly, it handles errors properly, and interact with obstacles as expected. And for end-to-end testing, these tests cover the complete workflow from sending a launch request to verifying the robot's position or handling errors, ensuring that all components of the system work together as intended. Our test scenarios are valid launch. It tests if a robot can be successfully launched into a one-by-one world. And invalid launch tests the system's response to an invalid command. Test robot name exists, checks how the system handles attempts to launch a robot with a name that already exists. We also have test in a 2x2 world. It verifies that 2 robots can be launched in a 2x2 world. Launching a robot with obstacle ensures that robots do not occupy an obstacle's position. And lastly, world with an obstacle test, launching multiple robots in a world with a predefined obstacle to ensure they avoid it. Our tools and setup, we use JUnit 5 for structuring and running tests, robot world client that connects to the server and receive requests, and server initialization that ensures the server is up and running before tests and cleans up afterwards. Test cases are based on the expected behavior outlined in the requirements, such as successful launching robots, handling invalid commands, and dealing with world obstacles. And we have scenario-based. Each test case is designed to validate specific scenarios such as valid and invalid commands, handling of duplicate robot names, and interaction with obstacles. The tests align with the desired behavior from a user's perspective, ensuring that the system meets functional requirements. To automate and integrate, we used CI and CD integration, ensuring acceptance tests are integrated into the CI/CD pipeline for automated execution with each code change. We have a README file. Welcome to the amazing robot world. And for our setup, it has instructions on what to do. Open your terminal and change directly to where your server code is located, and use this command to run the server. For running the client, there's also a command for running the client. Launching a robot. This is how you would launch a robot. There's a command for that as well. And you have to start the game by launching a robot into the world with a unique name. We have our help, where it basically defines all the commands and what they do. And to explore the world, we have the look command that scans and gather information about nearby obstacles, other robots, and potential threats. We have commands like fire, which is used to disable other robots and gain a tactical advantage in the game. And for you to win the game, you have to navigate your robot successfully through the world, avoid obstacles, engage effectively in combat, and achieve dominance to win the game. We have game rules for robot commands, obstacles, world exploration, combat, objective. And we welcome any contributions to the amazing Robot World project. If you like to contribute, you can follow these steps: fork the repo, make your changes, test your changes, submit a pull request.
One, does the demonstration showcase the implementation of the program designed for your program using SQL? So in this program, as you can see in line 17, we have a database file, and so this is a string that stores an SQL statement for creating tables for a worlds table, and this SQL statement is for creating a table for storing obstacles. And here we have statement.execute. We are executing the SQL statements, so that just shows that our program is using SQL. And we also have the world data access interface, which uses SQL. And so here's some SQL queries, and also here more SQL queries for working with the obstacle data access interface. Question 2. Does the demonstration showcase SQL code that is understandable? So for world data objects, you have these understandable. So this SQL is fairly understandable. For example, here, if someone might find the SQL query difficult, although it is rather simple, you could also look at the name of the method. It will also guide you. So it's select all from worlds where the ID. So it it fetches you, it gets you a world from the database based on the ID. Select all from worlds where name, so this one gets the world by name. Select all from worlds, it gets all the worlds. Insert into world name size, so this one you insert a world into the world table. Update world, this one changes certain properties of the world, so it could be the name, the size, and the ID of that world. And this one deletes a world based on the ID. So all the SQL statements are fairly understandable, they're pretty simple. Question 3, does the demonstration showcase the use of SQL functionality that optimizes queries? So SQL functionality in this case, which optimizes queries, is the existence of these annotations. These annotations provide metadata about the code and are used to give instructions to the compiler, runtime, or other tools. These annotations are used to directly map SQL queries to Java methods, allowing for a clean and efficient way to interact with the database. So we use these annotations to optimize our queries. Question 4, does the demonstration showcase SQL functionality that makes SQL code understandable? So these annotations are not only for optimizing our code, for making it more efficient, but they also help with readability, as we've sort of separated our code from the SQL queries stand on their own, which makes them more readable, and so they are not like mixed in with our code. And also you have the method names also guide you as to what those SQL statements mean. Does the demonstration showcase the necessity of each join SQL query? So in this program we didn't use the join SQL query anywhere. Does the demonstration showcase the use of SQL functionality that prevents integrity of data accessed by multiple users and processes? So with our database, only one client at a time. So database access is it isn't threaded, so only one client can make changes to our database at a time, and also the database management systems handle that. Does the demonstration identify methods of accessing data for your program? So methods that access data, for example, it would be restore world. So restore world will restore a particular world from our data, from our database, given the name. So the user provides the name, and then the restore world will then go to our database and then get that world. So for example, here we have first line 146 prompts the user for the name that they want, and on line 155 we are then using our data access object. So data access object got world by name. We could look at that. Query, here is the query which we looked at before. So select all worlds where the name matches our given name, so that allows us to get a particular world. So that is one example of data access. Another way of the program accesses data from the database is by using the another way that our our program accesses data is through the API. So the API, someone will send a GET request with a world name, then the API sends that request or the information about that request to our to our data access objects, and then that data access object would then call the aforementioned restore method, which takes in a world name. So that's one way in which, those are the two ways in which data is accessed in our program. Does the demonstration showcase good use of data sharing within the application? So data sharing within the application, one example of this is when you're creating a robot. So you have this robot constructor, it creates a robot, and then one method on line 61, it builds a robot. So based on the type, so a robot will have a certain number for the shield and the max shot, but then that depends on the type of robot, right? So based on the type of robot, if it's a shooter, we will then get the appropriate value from the shooter class for the max shields, and also from the max from the shooter class for max shots, so and so on and so forth. So this demonstrates data like sharing. So that's one sense in which classes are sharing data between themselves. And another way is when the server, sometimes it is asked to, when it gets the robots command, it is then asked to list all the robots. It will then have to access a list of all the robots, and that list, as we can see on line 183, is declared as so as we can see, the list of robots is stored on simple server on a list called robot objects, and the display headers class has to access that list. And also when the API has to add a robot, looking at API handler, when an API has to launch a robot, it will launched, it will also use the same, it will also add on, as we can see on line 45, a robot name, or line 46, a robot object will be added to the robot objects class. So that is another instance of data sharing, sharing data in our project. Does the demonstration showcase the underlying technologies that link databases and websites? So one of the technologies that is used to link databases and websites would be what we can see on line 27, Javelin. So in this case we are using Javelin for our API server, and that can be used to connect a website with a database. So the Javelin server is responsible for receiving HTTP requests and then sending back responses. So on line 39, so the server is kind of listening for post, for a post request of that form, and then it will behave appropriately. The behavior is hidden in a robot API handler in a method called launch robot. And then this one doesn't use the database, but get so you have Javelin, which is a technology listening for HTTP requests. Websites can make HTTP requests, so it can be used for that as well. And also you have world. Yeah, so you have, in this case, so the client, it could be anything that can make a HTTP request. It is asking for a world given a name. Then we will use the restore world method that is found in our data access objects, and that will return the world given the name, and then send that back to the to whoever asked, to whoever made that request. Does the demonstration showcase methods linking web pages to back-end proprietary applications? So again, we have Javelin, which can be used to link web pages to proprietary application. So in this case, our proprietary application is the code that we are running, that is the code we wrote in Java. So all our classes and everything. So Javelin is what would link us to out there via HTTP. Then we get the requests, and then those requests are processed in the Robot World API handler, and then that Robot World API handler is using code from other sections of the Robot Worlds. So Robot Worlds would be our proprietary code in that case. So question 11, does the demonstration showcase code that is commented? So in our database setup, we have comments. So for example, in line 17 we have an inline comment telling us that's the SQLite database file. Line 28 is telling us so we are setting up the database connection. Then we are registering, and line 38 registering the SQLite server. And then these are SQL statements to create tables, and then we execute table creation. So those are examples of comments.
Then moving on to section F, which is our documentation. Our GitLab page has a wiki page, starting off with our home page, which gives a brief introduction to our project, the project description, as well as links to the rest of our wiki, starting off with our client-server architecture, where we have a short description of our server-side program as well as our client-side program, with links to more information about them. Starting off with our server side, we have an extensive explanation and specification of our server side, which includes our world as well as the server side commands that the user would be able to use, as well as our configuration parameters. We then also have the client side information, which explains how the user is able to connect to the world, commands they're able to use, as well as what our user interface would be using. We have pages like the web API, for example, which gives an extensive explanation about how our robot world API layer would work, as well as our different get and post commands. For example, we have this post command, which is used to launch a robot into the world. We have the parameters, the request body, as well as an example of what the request body would look like. And if we take a look at the code itself, we have our robot world API class. And within it, we have a method server.post, which would take the user's post command and then call the launch robot function, which would then launch the robot into the world and give a response to the user. Our project makes use of the Maven file structure as well as traditional Java standards in how we name our functions and also how our functions are structured using camel case for variable names. We then have a few more pages outlining things such as our database, explaining the tables we have in our database, as well as how we interact with it using EOD SQL, making use of object relation mapping. And finally, we have our walkthrough page, which gives the user an extensive explanation about how to use our run server scripts as well as our run client scripts, all of the commands that's available to them, and the features of our program.